Yes, good morning. And thank you, Johannes, and thank you, the organizers, for giving me the chance to present my research here at this conference. So I'm working at the Max Planck Institute for Quantum Optics in the division with Emanuel Bloch with Ultracold atom in optical lattices. And today I'm going to tell you about our research, how we are studying with this system interacting spins, so following up on the topic that we had before, but in addition look at the doping of these systems and basically at the interplay between the kinetic energy of holes and the magnetic energy of those spins. The fundamental question that's been around in physics now for many, many decades is what happens when you dope an antiferromagnet? Experimentally, there's quite an idea of this. What is happening is quite complicated. A lot of things are happening. Most famously, one finds these D-wave high-temperature superconductors in materials where antiferromagnets get doped. But around that, there are many, many other phases in the terms of charge orders, the pseudo-gap, a strange metal. And on the other hand, we have a microscopic picture where we think, yes, magnetism, we have spins localized at sites, we have some holes from the dopings, those can move around, and can we understand from this picture what is happening here on the right with all these phases? And that has turned out to be really, really complicated. There are lots of great ideas, but there's no clear picture, basically, how to go connect the left and the right on this site. And as experimental physicists with ultracold atoms, we now set out to basically approach this problem from the right by making a problem that we can probe very well on the microscopic scale that follows these equations and then hopefully detect some of the physics that is visible on the left. So more concretely, we are interested in the question of what can be captured by the Hubbard model, because that is the one that we can naturally realize in our experiments. And then to use these as a quantum simulator, basically for the real electronic, strongly correlated systems. And our tool that we use here runs under the name of quantum gas microscopes. In two heroic experiments, more than 10 years ago, it was realized for the first time that one could see large arrays of neutral atoms, one by one, which are interacting with each other in an optical lattice and basically form a strongly correlated quantum phase, but one can probe it on the level of individual atoms on individual sites. This has turned into quite a field of research. Each time I give a talk, I have to basically add one more experiment here, and I'm sure I probably forgot one more. But apart from the fact that there are lots of beautiful colors that people use for coloring these pictures, I think I will hopefully convince you that there's really a lot of interesting physics that one can study with these platforms, where one has the opportunity to really see individual atoms and in this way come very close to the microscopic picture that one uses to describe things from the theoretical side. Here's a quick overview of my talk. So I will start to introduce our technical system of the quantum gas microscope, and then I will focus on a few projects that we've been working on, in particular a realization of a topological Haldane phase, and then going to the doped systems I was talking about before, both in 2D and in smaller lattice systems where we've realized to see something where two holes bind together. But first, let me introduce a team that's been doing all the work. So on the left, there is a lithium research team at the MPQ, with, of course, all led by Emanuel Bloch. And then on the other side, we have a lot of theory collaborators, which are very essential to everything that I'm telling you today. And a big thanks goes to them, because much of this research and what we're measuring comes out of these discussions that we're having. Okay. What exactly is a quantum gas microscope and how do we do this? Well, for this, let me first tell you about the Fermi-Hubbard model, which I probably don't need to introduce in this context. It describes as a minimal model how electrons can move in a lattice. So there's a hopping term, how electron hops from one side to the next. There's an on-site interactions only if an up and a down spin meet on the same side. And one can introduce a local chemical potential, basically some offsets that will become relevant later in the talk. And So it looks really simple, but it's actually really complicated to understand what's going on if one looks in particular configurations. At half filling, the situation is fairly simple. So here, the physics is given by the transition from a metal at low interactions or high temperatures to a mod insulator, where basically then the interaction energy is a dominant scale, and the system just orders, and one has one atom per site. And this is something that we can see in the lattice. So what we do is we take our ultra-cold gas of atoms loaded in a single plane of a three-dimensional optical lattice, and then we take pictures of it with special configurations. In detail, there's a lot of technical tools coming in here in the sense of Raman sideband cooling, making really deep lattices to hold the atoms in place, because taking these pictures takes on the order of 1 second. And the atoms have to basically hold still for this entire second. Well, once one does this, one can take pictures like this one here, and what you can see is that basically directly you can detect the individual atoms and the lattice sites, and we get a really nice resolution of where it's an atom, where there are two atoms, or where there are holes in the system. So we can digitalize these pictures, and this is then our starting point for all the analysis that I'm going to present from now on. And fundamentally, this is a really interesting observable because it's quite different to traditional physics observable, where one measures the expectation value of some operator. Here, it's really a projection of that many-body wave function that this state is in. So each time one sees all the fluctuations that are in the system, and basically one can then calculate based on this digital data, where one takes lots of repetitions of the same situation, the quantities one is interested in. So the simplest thing, of course, is to look at the density, where you just locally take averages. And for us, we naturally would end up with something like this, where basically there's some kind of confinement that pushes our atoms in the center, so the density is highest in the middle and lower at the edges. But we can manipulate that, and I will show you some more of this later. But then I mentioned that we see all the fluctuations. So what do I mean by seeing all the fluctuations? It really means that one can calculate something like a local variance and over all the pictures. So here is a description or a measurement of this. So we see the density going from an empty band to a completely filled band from 0 to 2, and because of the strong interactions, there's this dip here in the middle where the fluctuations are strongly reduced around the mod insulator. Theoretically, one could expect to go to 0. That would be the perfect mod insulator. But then there are some fluctuations which are inherent in the systems, quantum fluctuations, and if we add to that the imperfections of our measurements, of course there's some detection efficiency of around 97, 98, maybe 99% on a good day. And that then quite clearly matches to what we're seeing here. But those are only local correlations. If we go and then also non-locally correlate basically these pictures, we can in addition extract something like the sum of all the non-local correlations, and one can do like nice checks where one adds these all up and confirm some dissipation fluctuation relations, where compressibility, which we can measure independently, and the temperature basically match out. And so that's a nice confirmation that these pictures really basically contain all the terms, and we're not missing anything that is relevant over larger distances. But I was promising to talk about spins and antiferromagnets. So if one looks at the low temperature of this mod insulator at half filling, one finds that the system forms an antiferromagnet. That directly emerges from a second-order exchange process between neighboring atoms. And so one arrives at a Heisenberg spin Hamiltonian, which was just introduced in detail. So I think I can cut this a little bit short about the different phases that one finds. So basically, the amount of order reduces if you reduce the dimensions, because fluctuations in the system become more and more relevant, up to the point where basically the Néel order isn't visible anymore in one dimension, or mixed dimension or ladder systems, which is something I'm going to focus on in a moment. So in these ladders, basically, one can really see and parquet the system in what was just called a valence bond solid maybe with a few resonating parts. And to measure this, of course, now we need to see not only the density, but also the spin. So we managed to extend our system by doing local Stern-Gerlach splittings, so one can convert the spin information into a spatial information, which we can then measure with a microscope. In detail, this involves basically taking two pictures with different foci, which one can then overlap to get the full distribution of 0, up, down, or 2 particles per site. And then one can run these statistics. So here's an example in 1D. One finds very strong nearest neighbor correlations, but then a very fast decay. And this very well corresponds to the theoretical expectations at temperatures around 0.2 of the tunnel energy, or about half of this exchange energy J. So even at these, what I would call fairly low temperatures, but of course we'll see in a moment that what we're actually interested, the temperatures are much lower, these correlations are always quite short-ranged. So a realization like the one down here, where basically there's a perfect nail order, that's just very rare. But if you take a lot of pictures, you see it every now and then in a system of, I think these are 15 sites. We can do the same in 2D, so we see clear antiferromagnetic finite range correlations in these systems. They actually can spread through the entire systems. If we typically have system sizes of maybe 7 by 7 or up to 10 by 10, then one basically sees a weak correlation that stretches through the entire system, even at finite temperatures, because there are some finite size effects which are coming in here. So at the back of your mind, for what I'm talking now, you can think about our system as being magnetized to some degree in this antiferromagnetic pattern, but with some fluctuations, both thermally and from the quantum side. If we Fourier transform this, we do see a clear peak at pi of our spin factor. So how can we do something topological with this? For this, let me introduce to you the concept of a string-correlator. This is something that came up in the 80s to characterize phases which cannot be described by classical local order parameters. And the standard concept is that basically in 1D, in between the two operators that form your normal correlators, you introduce a string of operators which you have to measure at the same time. And this measuring at the same time, of course, shows you that this is something that we can in principle do with these quantum gas microscope, because we can get these snapshots and basically evaluate arbitrary orders of correlators, including an entire string, by just basically calculating it by hand from all the snapshots. So one just needs to find a realization where these A and B operators are something that we can measure. And the famous example for such a system is, of course, the antiferromagnetic spin 1 chain that was studied by Haldane in great detail, and has a very nice description. So if one looks at such a spin chain, it could look like this. So you have, because it's spin 1, up and down and 0 spins. But on the first sight, it might look quite chaotic because there's some pattern. But if you look closely, you see that every spin up is followed by a spin down, just with these zeros in between. And this is now something that, so there is some order in the system, obviously. It's just not so clearly visible on the first sight. And such a string correlator is now able to extract this. So if one just measures the spin Z and introduces this string here, which basically counts the number of zeros in between and adjusts the sign accordingly, one does get a finite system, even in an infinite system. For such a correlator, so it forms an order parameter for this system. And of course, spin Z's we can measure, so we've been keen to try this for a long time, but then, of course, the difficulty is that one needs to be able to realize a spin 1 chain with antiferromagnetic coupling, and we only have spin 1 half particles in our system. And here, a famous description of this model in terms of an AKLT splitting comes up. So one can describe these spin 1s as made up of 2 spin 1/2 particles, which are strongly bound basically into spin 1s. And then those are antiferromagnetically coupled such that they all form singlets between those. And so in principle, one could do a reverse engineering and say we have spin 1/2 particles, we locally couple them ferromagnetically to form spin 1 particles, and then that should give you the same physics as the spin 1 chain. How can we do this? Well, for this, I was mentioning I need to bring in these local offsets. So we can use a spatial light modulator to form arbitrary patterns into our systems. So we can basically block sites and by this create some kind of patterns. One of them that we can form is then also a ladder system where you basically have 2 spins next to each other and then they form a long line along the second direction. So how does this work in practice? Well, one programs these patterns onto these micromirror plates, put some light on them, images onto the atoms. Then there needs to be a lot of feedback for this to work properly because, of course, you don't really know what you're doing. But this can all be figured out, and then one can get basically snapshots of these ladder systems. So we made those ladders, and here you can see directly the analyzed spin correlations for nearest neighbors and diagonal ones, now spatially resolved over the system. One sees what one expects, so an antiferromagnetic nearest neighbor correlations and then ferromagnetic correlations along the diagonals. But of course, this system by itself, if I analyze it like this, there's nothing really topological about it. It actually just forms basically strong singlets, so that's a spin 0, and I just get a chain of spin 0s. But what one realizes here is basically the trivial partner of that topological Haldane phase. And a view into the literature gives you the right hints on how to basically proceed from here, because there are several ways on how one can take this completely antiferromagnetic Heisenberg ladder and still retrieve these topological properties that are present in the system if analyzed in the right way. So what we need for this is either a ferromagnetic run coupling. That's something that we used to not be able to do, so we first tried the second approach, but now I will later on also show you results where we managed to do these ferromagnetic couplings. The other idea, which is really neat, is to use these diagonals as your unit cell. So basically, you saw these ferromagnetic couplings on the diagonals, so if I use this to basically form my spin 1 particle, I get a description which maps onto the Haldane phase, this spin 1 system. So for this, we basically have to make diagonal unit cells, which amounts to just cutting your system diagonally at the edges. And then one can think of this like basically rolling up this ladder with the diagonal edges into the spin 1 chain. And so we did this, and then we analyzed the spin string correlator here, the one that I was introducing earlier. And yes, indeed, we find a finite value over our system sizes, which of course, one needs to say this is a finite temperature system, as I was saying before, so one can actually immediately expect a complaint that, oh, this is a phase that should only exist at 0 temperature, so how can there be anything at finite temperature? And then once again, the finite system size comes into play, because one can basically analyze and directly calculate in these systems of 7, 8, 9, 10 sides length of this ladder, that the overlap at our temperatures with the absolute ground state is still on the order of 50%. So basically half of the time we actually realize the ground state. And that means that we can still see these correlations which are only present in the ground state of the system. One can then look at the normal spin correlations without this string, and yes, indeed, those decay to 0 really, really rapidly, consistent with this picture of local singlets. And then we can also analyze a second correlator, which is a string-only correlator, which should be 0 in this phase, and it does indeed become 0. If we do the same thing in this trivial phase I was introducing before, where we do the straight unit cells, we see exactly the reverse. So this all matches the theory that one expects at 0 temperatures, just with different absolute values due to the finite temperatures. And the second main properties of these systems are that they should show edge states. So it's a spin-1 system, but the edge state should be of spin-1 half nature. And we can see those in the experiment by basically putting one unit of magnetization into the system. Because these edge states are free to point in any direction, the lowest energy state will always be the one for one magnetization where this magnetization sits at the edges, because there it doesn't cost any energy. While if I put it into the bulk, I have to break a singlet bond, that costs some energy. So what we see here in red is basically how this magnetization dominantly sits at the edges. And then, well, this isn't quite 0 because we're not at 0 temperatures. But it matches quite well. We can analyze the correlation to the edge state localization length in these systems by basically just fitting the magnetization pattern. And we analyze this then as a function of the parameters, compared it to theory. And one can see that basically for strong singlets in this direction, it's very short, because all the physics is very short. If we go into a mixed regime, these fluctuations come in and the correlation length extend. At 0 temperature, it would diverge here on the left. At the finite temperatures, we get a cutoff. We also check that this is actually independent of system size, which is quite neat because, of course, our system is quite small. And but it looks like because all the physics is local in these systems, we can actually capture the same physics that one would expect in a big system at a lower temperature. I think I will go and skip this part a little bit. This is how we make the ferromagnetic couplings. One can play with local offsets and basically introduce a small tilt into the system, put in some ferromagnetic couplings. We can measure the same things, and at the end, what turns out that in both of these situations, one finds these topological correlations, while in the first case, one has the trivial ones. Okay, with this, let me have a quick look at the time. I wanted to talk about the doped 2D system. And here the idea is that you go from this antiferromagnet in a third direction where you now add doping to the system. So holes or the particles can move around. This is typically described in the framework of the TJ model. And the first effect one can look at is basically for individual holes, how those can move in this antiferromagnetic background. And I'm sure you've seen this if you've ever looked at these kind of systems that, well, a single hopping produces these frustrated bonds. So there's an energy cost, and by itself, if you freeze the spin background, the hole is actually localized and can just run around. So this forms something that is called a polaron, which a magnetic polaron, which can then move only at a much lower speed than a bare hole in a non-ordered background. But for us, the special thing is we could look now with the microscope basically into the structure of this polaron. So if we filter our data and basically look around the random position of holes or doublons, one finds this changed spin correlation. So one can really see how around these dopant, the spin environment is completely changed. So on these diagonal bonds, basically we find now antiferromagnetic correlations instead of ferromagnetic correlations. And we can analyze this as a function of distance and find that this is actually a quite compact object, which is also expected because, well, the hole can hop further, producing more frustrations, but then the spin background isn't frozen. But there can be these flip-flop operations from the Heisenberg model, so this can actually repair the spin background. And with this, the hole can move. There were some beautiful experiments of this in Harvard in a similar system. And well, we looked at this then for different kind of dopings, and basically one can study all the different properties in the spin environment, so from the spin structure factor to how the spin patterns around the holes evolve as a function of doping. And what one finds is that basically there's two regimes. At low dopings to up to 30%, we find this polaronic behavior, and afterwards things are fairly well described by a Lattinger liquid. But keep in mind that, of course, this description and these measurements were done at fairly high temperatures relative to these phase diagrams that people are familiar with from like cuprate-like systems. So we sit somewhere up here, and much of the exciting physics should be at temperatures below that. And that's, of course, our main challenge, that we want to get colder, that we want to get to the regime where one can see some of this. Because what is it that one could expect there? Well, to go at some point to this collective physics, the holes or somehow have to interact with each other, right? So we have to go beyond this single polaron picture to something where larger phases evolve. So here we didn't see any of that. So we saw correlations about around pairs of holes if they spontaneously form, but there was no sign of pairing at these temperatures. And well, then there are two ways, basically, if one wants to see something for which one is too hot. So either we have to find a way to cool the system. That turns out to be quite hard. I mean, we have ideas for the future, but what we tried here is a beautiful idea to instead raise the binding energy of two holes in the systems. So let me quickly explain you this idea. And to make it things simpler, we go from the 2D model now into the back into the ladder. So we just have two sides in this direction and an infinite or finite size ladder in that direction. So if you think about these holes, well, one hole moves, that shifts around some of these spins, and that costs some energy. So that's basically unhappy. But the second hole could follow up and repair this, which leads then to some energy gain of two holes staying together. And the same mechanism should work in 2D. Just with different energy scales. So if one does this, basically the question would be, does this already lead to pairing of these holes on the rung? And the answer is actually no, at least for a very large parameter regime. This doesn't work. If you measure this is now a G2 function between two holes, so how their distribution basically peaks around the function of relative distance across the system here. And what we see is a strong repulsion for strong distances, which is naively completely expected, because those are fermions, and fermions just repel each other due to their Pauli statistics. And that effect is actually much bigger than this binding effect that you can argue here on the left in terms of the magnetic correlations. So this is where the trick comes in. So the Pauli repulsion. And then the trick is basically to reduce the kinetic energy of the hole, to just ignore, to turn off that Pauli repulsion across the rungs of the ladder by not allowing tunneling in this direction. And the neat thing is we can do this by a tilt between these two sides. So basically the tunneling in this direction becomes energetically forbidden. But the spin order still lives in 2 dimensions because the spin exchange processes are only slightly modified by this tilt. And now basically the holes are free to move only in this direction, and there's no energy penalty for sitting close to each other. So if we do this kind of system and measure the correlations, we do indeed see that the holes like to pair up. So this, I think, is a clear indication that, well, this magnetic picture that holes can bind due to the magnetic background that they're moving does indeed work. One just basically has to turn off some competing processes for it to work, or go to sufficiently low temperatures, because of course in these systems numerically it is established that there is some binding at the right parameter regimes. To confirm this in a bit more detail, we then looked at these things. So one can calculate the binding energy of this boosted system, and you see this is now about 0.8 of the J. This is about 10% more than our temperature, and with that we are basically can see it. We can increase the temperature a bit and see, yes, this effect goes away. And with this, I'm coming to the end of my talk. So in the future, we want to look and turn this, of course, into a full 2D system. So can one do these mixed dimensional things also in 2D, basically to use this boosting effect to also look at correlated holes in 2-dimensional systems. There are also some ideas on how to do this in bilayer, or even to use this to realize some frustrated spin models in the system. And with one last thing, which is a new project I'm about to end, which is that we heard a lot about quantum computing, so we were also thinking about how we can take these systems and turn them basically into a quantum computer to have some digital gates that come into play. So there are actually a few things one has to upgrade in this case. We have to introduce single qubit rotations, which should be straightforward in principle, because one can do Raman transitions on individual sites. And then we need to do 2 qubit gates, for which we actually have some clear ideas, and there were some realizations of this in other systems. So with this, we basically would have a system that could do both the analog simulations I was just presenting and some digital gates for state preparation, for readout, or as a full quantum computer. So this is a new project which we just started to set up. And with this, let me thank you for your attention. And I hope I didn't take up all the coffee break.
Yeah, thanks a lot for this nice talk. So we have time for a few quick questions before the shorter coffee break. Any questions? Okay, so then maybe let me start with one. So you showed us the results on these AKLT chains, and so these are at finite temperature, where, as you said, we wouldn't expect any order. So did you check actually then that the finite size scaling, and how, if you take different system sizes, how the order parameter would actually vanish?
Yes. So here you see an example. On the left is this calculation that I was presenting, which is basically giving you the ground state population as a function of the system sizes that we can realize, which of course drops, and for a large system it will always become 0. At fixed entropy per particles is where we did these calculations in this case. And then here the spin string correlators that I was showing for larger and larger system sizes. So I was mainly presenting these results about 7 sites, and then if one goes to 9 sites or 10 sites, one can see that the correlators are dropping, and here they're just barely above 0. So for larger systems, we both numerically and experimentally expect this to basically go away at these temperatures. But it's always a trade-off. So basically, there is a clear scaling of the system. So if I reduce my temperature while I'm making the system bigger, or I can also say I just need to keep the total entropy in the system constant in this limit. And the total entropy in a small system is not that big, so this is why it works.
Okay. Yeah. Other questions? Yes, please. Yeah.
A very basic question. How do you measure the temperature?
Yeah, we cannot really measure the temperature directly. What we do is we compare observable to calculation. So our main thermometer is typically the nearest neighbor spin correlation, which we then compare to. Well, in the undoped system, it's straightforward because one just has numerics there. In the doped system, so far, in these small systems, we could run some DMRG code and compare to those. If you go to the full 2D system, of course, this starts to become tricky because the calculations get very hard. And then that is a somewhat open challenge, basically, to come up with good ideas how to get the temperatures. We can, to some extent, maybe live from the fact that if we have a thermalized system across the entire system, we can have wings of the distribution, which then have easier physics because of lower densities. So that is something that people traditionally do when you have a correlated system. You look at the low density wing of your distribution, and that one you can calculate. Of course, we like to separate those, so it might not work in this case if one does these entropy management methods where the center might have a different temperature. But it's a very good question.
Yes, another question there.
Hi, Timon. Thanks for a nice talk. So I think I've asked you this a couple of times, but what is basically what is limiting you in the temperature of how low you can go? What are the major limiting factors?
Well, this is a bit of a discussion. So the traditional picture that people put out is that cooling fermions is hard because you form this Fermi C, and so you have a lot of state. The temperature is only given by the edge of that Fermi C, so this is still in the bulk. And now if you lose a few particles deep inside your Fermi sea, just because of background collisions, that is a massive heating process, because that rethermalizes and basically heats up the entire system by a lot, even if you use just 1 or 2 particles. And that doesn't happen with bosons, where you form a BC and you lose a particle from the BC and you don't care in terms of your temperature. And so that's one point. The second point, of course, is that it's very hard to cool the system once you're in the lattice. So because you cannot really evaporate, transports are slow, and it's just hard to basically get the entropy out of the system once you're in the lattice. So basically the combination of those two things. And there are some ideas which run under the name of entropy management, where basically you have the remaining excitation in the system and you try to push them somewhere which you can later ignore and then have a very pure system basically in the center. So this is what we're trying here, for example. So the center here is basically has much lower number of excitations compared to this wing of particles.
Okay, good. Thank you. Then let's thank our speaker again.